So this video is about a property that a collection of vectors can have called linear dependence. Let's start by writing down a couple of things that we know. So we know that the span of two vectors is a plane unless they're collinear. And we also know that the span of three vectors is a three-dimensional space unless they're coplanar or perhaps even collinear. And then in those degenerate cases, when these three vectors are coplanar but not collinear, the span will be two dimensions, so a plane. And if they're collinear, the span will be a line, just like would be the case if we had two vectors that were collinear. It's in these degenerate cases where we're having a collection of vectors, in this case two or three vectors, but we could be talking about higher dimensional things or larger collections of vectors. And it's those kinds of collections of vectors that are exhibiting this property of linear dependence. So let's write down a definition. A set of vectors is linearly dependent if one of them can be written as a linear combination of the others. So let's look at a couple of examples to see how this actually works and what it means. So for a first example, let's pick something pretty simple. We'll work in two dimensions and take two vectors. Now this is a set that exhibits this property of linear dependence. And the reason we can see that is because we can write one vector as a scalar times the other vector. So that's one example in two dimensions. Let's look at an example in three dimensions. So here I'm going to take v1 to be 1, 2, 0, and v2 to be 2, 4, 1, and v3 to be 0, 0, 5. And this set is also linearly dependent. And the reason for that is I can write one of these vectors as a linear combination of the others. So for example, if I take the vector 0, 0, 5, I can write that as 5 times 2, 4, 1, which is v2, minus 10 times 1, 2, 0, which is v1. So what I have here is that v3 is equal to 5 times v2 minus 10 times v1. Since I can write v3 as a linear combination of those other two vectors, I know that this collection is linearly dependent. Now the next thing we want to see is probably what's the geometry of this. So let's take a minute to draw a couple of pictures. If we plot the vector 2, 4, that is going to be the arrow that points to here. And if we draw the other vector on here, that's the vector minus 1, minus 2. That is the arrow that points to here. And we can see, as we expected, that one of these vectors is a scalar multiple of the other, right? These are both lying along the same direction, right? They lie on the same line. They're collinear. And so they're linearly dependent. So in the next example, we have to draw in three dimensions. So let's draw these three vectors starting with v1. So v1 has x1 component 1, x2 component 2, and no x3 component. So this is a vector that's pointed at this point, and it's fully contained in the x1, x2 plane. Now, skipping ahead to v3, if I draw a picture of v3, it's got 0, 0 for the x1 and x2 components. So I know it's going to lie on the x3 axis, and it's going to point right up here to x3 equals 5. And that's our v3 vector. So now let's look at v2. That's the one we have yet to add. Now v2 has the first two components, 2 and 4. Right? So if I plot that 2, 4 in the x1, x2 plane, I can see that it's along the same line as v1 so far, right? So it is actually, if I write it in the plane like this, just 2, 4, that would be on the same line that is containing 1, 2, 0, v1. But now instead of stopping there, I have to go up 1 unit to get this x3 component, which is 1, but I'm still kind of paralleling that blue line. It's like I just took a longer version of the blue arrow and rotated it up. Now, all three of these vectors are in the same plane. They're coplanar, and that, just like these two vectors being collinear, is what the idea of linear dependence is trying to catch. It's sort of like you have more vectors than you need to describe the subspace. We really only need two vectors to describe the space that these three vectors lie in, this subspace, but we have three. And so when there's extra ones, that's the notion that linear dependence is trying to capture. So now we've seen the geometric interpretation of linear dependence. Let's see what this looks like when we think about it from an algebraic perspective. So I have this equation, v3 is 5v2 minus 10v1, and I can rearrange it with just a couple of steps of algebra to get this. And now when I have this, and I've got all the vectors on the left-hand side and a zero vector on the right-hand side, this starts to look like, to me, a linear system. So let's write that down. And it's not just any old linear system. This is a homogeneous linear system. It's because this linear system has a non-trivial solution, that is -10, 5, -1, that there is a linear combination of these vectors that equals 0. So if we just took one of the vectors to the other side, we'd end up with an expression of one vector in terms of the others. So let's make an observation and look at this a little bit more generally. If we have a set of k vectors in n-dimensional space, and the matrix equation has a solution that is not 0, then the set of vectors is linearly dependent. Since we know something about homogeneous systems of linear equations, we can actually make a couple more observations. So let's think about this a bit. So our homogeneous systems are ones that have right-hand side equal to the 0 vector. So they always have at least one solution. And if a homogeneous system has more than one solution, it has infinitely many solutions. And if we set up a system like this that's got vectors as the columns of our matrix A, and 0 is the only solution, then our set of vectors is not linearly dependent. But if there is one more solution, if there's a free variable, when we solve the system, then we'll have infinitely many solutions. So maybe let's check out at least one situation where we can kind of glean some information about homogeneous systems and the interplay between dimension and the number of vectors that we have. So let's imagine this case. What if we have more vectors than dimensions? In other words, n is less than k, right? Coming back up here, we have a set of k vectors in n-dimensional space. Well, it's always helpful to, instead of thinking about something straight out of the gate in a very abstract way, let's imagine a particular pair of sizes that we can actually compare. So let's say we're sitting in three-dimensional space and we have 4 vectors. So in that kind of situation, what our linear system would look like is 4 vectors as columns of a matrix. And I think instead of using v1, v2, so that I don't have to do double indexing, I'm going to use vector t, vector u, vector v, and vector w. And this is a matrix that's got 4 columns, so this has to have 4 rows. And this is the homogeneous version, so we're setting it equal to 0. Remember, what this is really saying is that A1t plus A2u plus A3v plus A4w is equal to the 0 vector. Now, to see where the linear combination thing comes in, you can just imagine rewriting this. So we had A1t is equal to minus A2u, and so on, right? Just bringing everything to the other side and then dividing or multiplying by scalar 1 over A1 if we need to. And then we have an expression for t in terms of the others. So now if we're taking vectors from 3 dimensions, then that means this is a matrix with 3 rows. And then of course we have 4 columns. But if we have 3 rows and 4 columns, think about this now as what it is. It's a linear system. If T is a vector in 3 dimensions, it has 3 entries. U has 3 entries. And V has 3 entries. And W has 3 entries. And we're multiplying this again by A1, A2, A3, A4, and trying to see if we can find a non-trivial solution to this system. Well, imagine doing row operations and getting this into echelon form. Right? If we're going to do row operations to get this into echelon form, we're going to have the staircase of zeros, and we're going to have at most 3 pivots. Well, there's 4 columns, so that means that there has to be a free variable. We know the system's consistent because it's homogeneous. So I could just plug all a's equal to 0 and I would get a solution. But we're looking for a non-trivial one. And since there's a free variable, that means that there are infinitely many solutions. So if there's infinitely many solutions, there's definitely a solution where not all of these things are 0. And those are the exact coefficients that we'd end up with in our linear combination that would give us 0 and allow us to take one vector to the other side and scale it so that we have one vector written in terms of the others. So that means that this set of vectors is linearly dependent. So what's the lesson here, right? What's the conclusion? Well, one conclusion is that if we have more vectors than we have dimensions, right here we had 4 vectors and 3 dimensions, then we necessarily have a free variable because the number of rows is smaller than the number of columns in the matrix that we're setting up. If on the other hand we have more dimensions than vectors, or we have the same number of dimensions as vectors, then we don't know. Could be a linearly dependent set, might not be. And we'll talk more about that when we talk about minimal spanning sets. But let's stop here for now.